Hey, good morning or afternoon.
Ken, there you are.
Hey, Ed. How you doing?
I just dropped you an email because it was giving me a little bit of static when I tried to join.
Yeah, the TOC just ended, so it took me a few seconds to jump over.
Okay.
So
All
I
good.
am not sure about when I arrive in Austin yet. I'm going to be in India the week before.
Mm-hmm.
And so just be coming back from India and trying to figure out how I get to Austin and when I can get to Austin. So I'll try to get back to you still this week on your request for the FIDO meetup.
Much appreciated, and I completely understand the travel issues. So Austin, the one thing Austin doesn't have going for it is it does not have a world-class airport in terms of connections.
Yeah, that is so true. Hey, Chris, how you doing?
Pretty good as soon as I find the mute button. How are you doing?
Doing well.
Yeah, Austin's always a hop.
Yeah, it's the only thing that isn't amazing about the place. So.
Yeah. I've even yeah, anyway. Yeah, it is. So I fly American, so it's not horribly painful. It's just up and down from Dallas, but still it's an up and down.
Yeah, no, American has played some funny games there over the years. They used to run directs a lot out of Austin to places like San Jose. And they were,
yeah, you know why that was, don't you?
Why?
It was called the IBM Express. So it was actually a flight that was Raleigh, Austin, San Jose. And I was on it quite a few times, early 90s, and you figured it out the minute you walked on the plane, and everyone had the ThinkPad on the plane.
But even after that, so in the 2000s, they were running multiple 737s a day from Austin to San Jose, and they were always jam-packed.
Yep.
And suddenly suddenly America decided all those flights had to go to Dallas, and it made no sense.
Yeah. No, but where that came from, I think, was literally was a half an hour change when they were doing it in Austin. So it was just people on and off the bus and continue on the way. But yeah, that's all gone now. That's all gone now.
Yep. Cool. So should we allow a few more minutes? There we go. We got some more folks.
Sure.
Yeah, I think we should allow a few more minutes. I know the TOC, like I said, just ended.
Yeah, and then there were some complications getting on at the accustomed time. Good morning, Lee.
Morning, Lee.
Gentlemen, good. Happy Tuesday.
Indeed.
Hey, Ken, nice work. Well.
Thanks.
Yeah. I particularly enjoyed the absolutely insight.
Yeah, I've never been involved in a work group where they battle over that much over a word.
So you've never done IETF, Ken? That was actually those battles can go on across multiple working group meetings.
Yeah. The IETF, though, they kind of trumped you with that, we got to see it working. So there might have been a lot of debate, but you always knew in the end you had to produce something that could interoperate.
Yeah,
that seemed to help cut down a little bit of the banter over the meetings.
That used to be the case. It hasn't been anymore because everyone just does it as experimental or individual contributor or whatever else. I mean, as long as you don't want to be on the standard track.
Right.
The days of proving interoperability, unfortunately, are long gone. It would have made things so much easier to just put everyone in the sin bin, but
right.
Too many vendors.
There's some other interesting things that are starting to come up in the IETF. Their hackfests are getting to be quite fun lately. So, I mean, a lot of what we've been seeing sort of is they'll have a hackfest at every IETF, and every IETF we wind up with some protocol or other that gets implemented as a plugin to VPP. ILA won Best in Show at one point, for example. And so you wind up with really cool stuff that actually makes it into code and into the real world pretty fast.
Mm-hmm.
Yeah, I think that is a very interesting use case of hackathons. I like that a lot. I'm trying to get MasterCard here to do more hackathons because their idea of innovation is drinking a beer and talking about how fun things could be. So
that is a critical first step, but
yeah, I told them we could do that and have pizza and do something. Then they were like all excited,
It is important to remember that coding while drinking there's a fine line there, especially in the comments.
Yeah.
Hey, I didn't say we're gonna be in production, did I?
That's why they're called hackathons. Yeah.
Yeah,
I mean, oftentimes that code actually just works. The problem is someone trying to figure out how you got it to work later is the more interesting aspect of it.
yeah, see, I have an oversensitivity to the content of the comments because I've often been involved in we wrote this as closed source, now we're going to open source it discussion.
Yeah.
You go through and you walk through that and you're like, oh my God, we've got to trim the comments. So
Cool. I think I don't know why we're getting less and less people at this event, but maybe I need to do a better job of advertising for it.
I made some attempt to promote it on Twitter, but
we're getting. I see.
I'd say we have a
Carol
quorum here. There's all four of us are here. Let's just make whatever decisions we need to make, and you guys weren't there.
Yeah, we do. We do at least have a quorum, right? There's four of us. Yeah, 5 with quorum. So
when you're telling me you're going to revive IPX.
Oh, excellent!
I think
I think
I was thinking Fiddy and tokening would be better.
DevNet, come on, guys! DevNet Phase 4.
I want to go back to a token.
Dude, I'm a string theorist by training. I remember DECnet.
Yeah, ESNet probably still has some DECnet Phase 4 running somewhere.
Yep.
Yeah, in Austin, I'll tell you guys about this recent fun thing I've had here at MasterCard with China. They were using some old DoD addresses that me and another coworker here in the security side know from way back in the day that you guys would laugh at, but I can't tell you anymore on the phone.
So you guys stole SIPRnet again? Everyone abuses SIPRnet.
Oh, this was in China. This was the Chinese are doing. They thought it would be fun to reuse IP space for my DoD segments. Which I think there is some humor in that, but I didn't find it at the time to be humorous.
So before we get head into trouble with the DoD, let me go ahead now.
There is a service provider that when I was at Alcatel in New Zealand that shall remain nameless, that what they actually decided to do was number their ops network, their backend ops network by area code, equivalent of dialing code. So they used Net3 for stuff in Auckland, Net4 for stuff in Wellington, Net7 for stuff in Christchurch. And then they couldn't figure out why they were having problems getting to Apple, for example. And it's like, these addresses actually have meaning outside of music.
That's hilarious.
All right, let's get to work.
All right, so with that, Ed, I'm going to hand it over to you to talk through FDIO and VPP in terms of networking as a data plane for microservices.
Yep. And so let's keep this very conversational, which I imagine will be like pulling teeth with the crowd that we have here. Feel free to stop me at any questions. I'm going to basically run through a really quick what is FIDO, and then a little bit about the technology, and then show how it becomes applicable within CNCF. Can you guys see the share?
Yeah.
Cool.
Yep.
And some of the things that are possible with it, which there's a lot of stuff that can be done that you literally don't have anything else that can do. So really quick, FIDO, FD.io, we pronounce it FIDO because it's cutesy like that, and it gives us excuse to do things like I'm told that we actually have approval now to have a real dog at our booth at KubeCon. So we come by and see the puppy. So it's basically, it's a project of the Linux Foundation. It's open source. It's multi-party, meaning there are many people involved, and multi-project. All this is a familiar sort of structure with people like you guys at CNCF, which is much the same. It does a software data plane, basically. So high throughput, low latency, lots of features, very resource efficient, works equally well on bare metal VMs or containers because it's a pure user space data plane. So if you need to stick it in a container, sure, why not? And it's multi-platform. It runs on Intel, ARM, and PowerPC. At some point in the historic past, it ran on MIPS, but I don't know that anyone actually cares anymore about MIPS. So, and then we have a little bit of a rubric that we use to discuss the scope of things that live within FIDO. So we usually will talk about 3 layers. The first is network I/O, which is how do you get a packet from a NIC or a VNIC to a thread on a core. So you could think of this as something like DPDK, which does that brilliantly. And we actually use DPDK for that purpose at times when we're dealing with physical hardware. Then you could think of it as packet processing as the next layer. So how do you classify, transform, prioritize, and forward, and possibly terminate packets? And then, of course, now that you've got this spiffy packet processing going on, you need some kind of data plane management agent to manage it all. And you can kind of think of this as control plane, but we discovered the control plane meant routing protocols to a lot of people. And so while it certainly encompasses that, this is also the layer you would put things that, for example, would manage information discovered in that CD. Make sense so far?
Yep.
Cool. In terms of where it fits in, go ahead.
Oh, Ken, I'm sorry, not Ken. Ed, are we on, you're still on the first slide, right?
That was the second slide. It's titled FIDO, the Universal Dataplane.
Oh boy, is everyone else seeing the second slide, or is it just me
I am seeing only the first slide, actually.
Hang on. So the share is screwed up. 1 second. Let me try and reshare and see if that helps.
Okay.
So you should now be on FIDO, the Universal Dataplane.
Yes.
Yep.
That was the slide I was just talking to. Thank you for bringing that up. It would have made the rest of the calc much harder to follow. There's the graphic. Well, the graphics really do help in places. There's some fun animations on how the technology works. So moving right along, can you all see FIDO in the overall stack here?
Yes.
Yep.
Right, so you've got things like Kubernetes that handle orchestration. Then you sort of have data plane services from a networking point of view. This data plane management agents, packet processing, and network I/O, and that's sort of what FIDO is doing. And then, of course, obviously, you want to run it on operating systems like Linux, and maybe you have OCI speccing out your hardware, that kind of thing. There's pretty broad membership in FIDO, so we've got a bunch of service providers who are involved. There are network vendors, chip vendors, and various integrators as well. There's a lot of interest because this solves a lot of problems for people in data plane in terms of software. And then we've got even broader contribution coming in. So code is coming from a lot of different directions. And if you sort of look at the code activity, one of the things you'll notice is from a commit point of view, FIDO is currently probably the most active data plane community on Earth. It sort of has been rapidly outstripping what we're getting coming in from OVS or DPDK. And we've got a pretty broad set of contributors and organizations contributing as well. I'd mentioned that it's multi-project, so we end up having a lot of different projects that go into it. I've sort of classified them here by what's going on. Most of the projects in packet processing tend to be either VPP, which is the core technology, or things that are providing plugins or libraries to control it. Of particular interest to this group probably is going to be the Go VPP project, which provides Go bindings to VPP. So if you want to go build an agent to drive the data plane in Go, you just pick up the libraries and away you go.
I guess add a quick question there, just to clarify. Honeycomb, is that like honeycomb.io?
No, it's not honeycomb.io. So honeycomb is a particular data plane management agent. VPP is agnostic as to data flow management agent, so you can build whatever you'd like. Honeycomb is the one that service providers tend to like because it gives netconf yang interfaces to the functionality in VPP, and service providers love netconf yang. And so if that makes you happy, then it'll be a great data plane management agent for you, and if it doesn't, then pick another one.
Got it. Okay.
Cool.
I have a question about the Golang VPP. This is Kural from Intel. So I want to know how much contribution or how much projects, open source projects have been developed so far on Golang VPP actually.
So in the Go VPP library, there's a framework project called Legato, which was basically building out a framework for building data plane management agents. Because if you look at it in terms of wanting to build not just infrastructure stuff for things like Kubernetes, but also VNFs that you may deploy, you're going to want to build an agent for whatever VNF you build. So Legato is using Go VPP, and then there's some effort right now, and you'll see this in later slides, that uses the Legato framework to basically build a vSwitch VNF and literally treat the networking for Kubernetes as just another microservice. So it's just like any other microservice you run.
Okay.
But you jumped ahead a little bit. You'll see more of that as we go along.
Okay.
Cool. So, pardon me. At the core of the Fido project is this really cool technology called vector packet processing. Basically, it lives at the packet processing layer. It's incredibly high performance. It's pure user space, so you can run it in Linux user space. As I mentioned, it runs on Intel, ARM, and PowerPC, but it actually does some very sophisticated optimizations in order to run really well on them. It's a very mature technology. It's something that's shipped at volume in both the server and embedded products since, I believe, about 2004. So it's a very mature technology with the kinds of things that you want in a mature technology, like high-level, like really, really good traceability, hundreds and hundreds and hundreds of statistics on everything being collected without actually impacting performance, that kind of stuff. So the interesting question is sort of how does it work? So basically, it decomposes packet processing into a directed graph of nodes. So you can almost think of each of these nodes as sort of a micro network function. And each of these nodes does a very small amount of work involved in processing the packet, and then it hands it off to the next node in the processing graph. Now, packet processing graphs are not particularly new. What is new is that VPP processes this graph a vector at a time. So it takes a vector of packets, as many as it can take off of the receive queue, and it will take that entire vector and process it through, say, the Ethernet input node. And then it will move on to the next node from there. And this ends up doing some pretty incredible stuff to performance because a graph node is optimized to fit inside the instruction cache. So you wind up with a situation where the graph node itself, the first packet warms up the instruction cache. So after that, you don't have to go out to memory for the instructions. The packets are prefetched into the data cache. The lookups for routes or whatever are prefetched into the data cache. And the net result is that more or less after the first packet in the vector, you never actually end up blocking on memory, which gives you a massive speed up in terms of the processing of packets. And I've got some more slides digging into that with a little more detail here coming up next. So if you sort of visualize it this way, so you've got the packet processing graph, you've got the individual graph nodes. Some of them are input graph nodes, so packets come in from AF packet or vhost user or DPDK at those graph nodes. And you have a whole vector of packets. You can sort of visualize what happens. They come as an entire vector, node by node, through the graph. And so you get all those nice cache warming behaviors that I mentioned. In addition, you get the advantages of prefetch to memory. There's a lot of stuff being done with instruction parallelization. I think on the new Skylake server CPUs, the theoretical maximum parallelization of instructions per cycle is 5, and we're running something like 4.97 if memory serves. So hyper efficient. Now, a question should be occurring to you guys at this point, which is, basically, what happens if the vector splits? What if the vector of packets doesn't take a single path through the graph? And the answer is that essentially the vector can split at a particular node, and then it just gets processed from there as two different vectors. You can sort of think of this as an unlucky vector. This is sort of a into everyone's life, an art packet must fall. And it does slow things down because now you have two vectors instead of one being processed through the graph. But there's this interesting statistical property that allows you to catch up really quickly, which is because this initial vector took longer, that means that the number of packets on the next vector is a little bit larger. And since you have a bunch of these very expensive fixed costs, like hitting memory, that are being averaged across the entire number of packets, if n goes up, the average number of CPU cycles per packet goes down, and so you catch up. In other words, if you get a situation where things go a little bit more slowly for a couple of nanoseconds, they go faster the next couple of nanoseconds. Any questions so far on the quick run through the technology?
Nope.
Cool. So VPP also has a plugin architecture that's incredibly rich. So you can do anything with a plugin except resize the heap. So you can add graph nodes to the packet processing graph. You can rearrange the graph. You can build your plugins independent of the VPP source tree and just drop them as .so files in the plugin directory. And what this means is anyone can extend VPP with new features however they would like to do it. You don't have to block on everyone catching up. And likewise, you can use the same mechanism to provide hardware acceleration. So if I have a piece of hardware that handles some of the things that the graph nodes would otherwise handle in software, I can simply let it do that work and then skip to the place where software has to process in the graph. And what this means is if you have accelerating hardware in your boxes, you can simply provide plugins for them. And then if the hardware is present, things go faster. If the hardware is absent, then things still go. Or if you have hardware from different vendors and different hardware nodes in your system, you could simply stack up the plugins and say, okay, I'm not going to have to worry about differential deployment across different kinds of hardware. I just deploy one collection of plugins everywhere and take advantage of the hardware acceleration that's present. Make sense so far? Cool. Programmability, I'll go through this really quickly. VPP for programmability uses a shared memory message queue. It's incredibly high performance. It's been clocked in at 900,000 requests per second. Don't ask me why you would need to do that, but people who do high performance coding are kind of obsessive about making things fast. And then you get async response messages, of course. And we've got bindings for C, Java, Python, Lua, and Go that are being automatically generated every time we build. And Honeycomb, as I mentioned before, is just one example that takes this API and exposes netconf or restconf northbound. It turns out that anyone can build an agent, and so you can have any control plane that makes sense. So for example, when we start looking at the Conti VPP work that's being done, they're literally just building an agent that manages VPP and deploying it in a container as a microservice to handle the networking on the particular node. Performance. So VPP has been clocked in at a terabit per second on commodity servers with no hardware acceleration, with millions and millions of routes in the routing table. So I don't know anything else that even comes close. And when you sort of, yeah.
You know what's funny, Ed, is every time I come off mute, I guess it makes a noise, and so maybe that's just, it works out to my favor. Question here then. Given that VPP runs in user space, but also acknowledging that if certain hardware is present, packet processing will be accelerated. Is it fair to assume that this is public cloud friendly?
Oh, it's extremely public cloud friendly, yes.
Okay.
Extremely. Because again, it'll run, it will run whether or not you have magic hardware present. So it's very friendly to public cloud. And it's even friendly to, you have some funky networking thing that you need to do inside a container. Well, with VPP, you don't have to go get the appropriate version of the kernel with the appropriate magic feature going. You can just run it purely in user space. which makes it not only very very friendly to public cloud, it makes it very cloud native friendly, because literally you've converted your networking into a pure microservice.
Okay. As people deploy, as applications deploy and take advantage of VPP, do they do that? They do that with VPP in the container image that they're using to run whatever.
Depends on what kind of applications you're talking about. So if you're a service provider and you're running to deploy a VNF, where the VNF is doing network processing, right? It's processing packets. Then you would probably want to build an application that has VPP inside it to do your packet processing. If you are just a plain old vanilla flavor application running on a Kubernetes node, then as you'll see here in some later slides, you can simply do the traditional dance of kube control apply -f vpp.yaml, and that will make that switch. But what will be happening under the covers is literally a VNF for your vSwitch, a container for your vSwitch, a pod for your vSwitch being deployed as a daemon set, so that your networking vSwitch is running purely in user space, and then your containers for the pods that you're deploying on that node are being plugged into it.
Okay. Okay.
I've got some pretty pictures around that because it is an interesting thing.
Good.
Yep. But so again, getting back to this, the VPP guys actually do count cycles per packet. So this was doing a comparison. We're making about 160 cycles per packet, which is damn fast. And I apologize, I misquoted. We're at 3.28 out of 5, not 4.97. It was the line below it that got stuck in my head in terms of the instructions per cycle. So, and we're literally
sorry to interrupt you. Just to make sure I understood this in the right way, when we were talking about given vectors being broken up and part of that processing being on, am I thinking of it in the right way that to the extent that a vector is broken up, that's it's the instructions per cycle that affects, like that's the number of instructions?
Not quite. So if a particular vector gets broken up, then what'll happen is you'll be running, so let me go back to the picture because it makes it easier to explain. So if you look at this picture, splitting the vector, so when that packet gets broken up, packets 0, 1, 3 through n, they process just as fast as normal, but you've got to go back and then load the ARP input node into the instruction cache to process packet 2. So the totality of that vector will process more slowly. That means the next vector is like n plus m. It's a little bit bigger in size. So your average cost goes down per packet for the next vector. It turns out statistically most vectors traverse a single path through the graph. But you do get outliers, but then you get the statistical effect that causes you to catch up. Make sense?
Yeah.
Cool. Let me catch back up to the slide deck. So, so you end up with extremely high performance. One other thing to mention here is we are literally finding that the limitation is the number of PCI lanes. We could actually do better than these numbers with VPP if we could get more PCI lanes from Intel. And the way we know this is back on the old, the previous version of the Xeons, when we were getting 560 gigabits per second, the telemetry was telling us it was the PCI lanes that were limiting us. And we're seeing that same telemetric signature looking at the telemetry now that we're basically pushing a terabit through. And so we're pretty sure that if we, as the generation of processors get better and we get more PCI lanes, we'll continue to see performance improvements, because these two numbers are exactly the same binary. It's just different hardware with different number of PCI lanes. So the sky is really the sky is pretty much the limit. In terms of features, this is kind of an eyesore. Basically what it comes down to is you've pretty much got everything you could imagine in terms of networking features if you were doing an industrial grade router or switch. You have in VPP. So routing, switching, advanced features like segment routing, NAT features, all the kinds of proxies you'd want for DHCP, lots of in-band telemetry, lots of counters, even support for things like MPLS if you want it. So you can do all kinds of crazy things with VPP. And that number continues to grow. And if there's anything it doesn't do that you want, it's a few hundred lines of C to write a plugin that does it.
So Ed, a couple questions for you real quick. Are there any reasonable limitations on, say, ECMP multipass, or do you really not care how big the hash is?
I would have to go find out what the outer limits really are, but I'll tell you a story that'll give you some idea of how the minds of the people involved work. Dave Barrick is sort of the genius behind all of this, and I was having a conversation with him at one point where he was sort of saying, you know, you really want in caps, not tunnel interfaces, because interfaces are expensive, you know, and they'll reduce performance, but you got to use them if you're going to do sort of a virtual bridge domain, right? If you're going to do a bridge domain for L2 stuff, you got to use interfaces and it has costs. And this kind of concerned me. And so I said, okay, Dave, so where are the walls on this, right? How bad a problem is this? And his response was, I wouldn't expect any kind of reasonable performance with more than about 80,000 tunnel interfaces.
Yeah, God help if you do a type of show int. Just a couple other questions, and I'm just looking at this. So the multipath was one. The other IP and IP, do you have that as an in cap?
I don't. I'm trying to remember.
I'm looking, and it doesn't look like it. And I guess
we have IP and IP, but quite honestly, in caps are the simplest starter problems we have if somebody wants to write code.
So I guess the interesting thing for the in cap is the way we use IP and IP in Calico is we do it stateless. We don't set up the tunnels a priori. We basically use the next hop address as it's a Linux kernel behavior. We use the next hop address as the endpoint of the IP and IP tunnel.
You're going to love this because essentially, remember the comment, you only actually use tunnel interfaces for the L2?
Yep.
So you guys are pure L3. In this case, you would just have a route that says, by the way, please go in cap this damn thing.
Yeah, so that's what we sort of do today. In Bird, we basically send it to the ton0 interface as which handle is the in cap stub, right? So I guess the only other one that comes to mind, there was two others. So I guess one was that, you know, what is the size of the multipath? And B, have you guys looked at doing V4, so sort of like bidirectional stateless XLAT, or some kind of XLAT, because XLAT performance in the kernel has been pretty horrid.
You have some support for XLAT. I could go get you the details on that. So
if you could, that would be great.
Yeah, I absolutely will. The one thing I will plead with regard to this slide is there's a lot of stuff that didn't get put on this slide simply because the number of features we support has made it impossible for this slide to actually be kept up to date. You know, and you know, this is the third attempt at this, and the last time I did this slide, it was like I simply can't fit anything else in here.
The reason I'm asking about XLAT, and I think this is larger for the network working group, I'm starting now to run into folks who are going directly from IPv4 only to wanting to run an IPv6 only infrastructure because they're just out of addresses. Yep. And Kubernetes makes it much, much worse. And then there is the concept of V4 as a service across the infrastructure. And you could do something like a stateless 4x4 XLAT to offer V4 as a service without requiring consistent V4 endpoints.
Yeah, I believe we do a standard. We do have available a standard V4, V4 over V6 XLAT. But one thing I will draw your attention to is we also have features like map and lightweight 4/6 that give you probably more complicated than you want, honestly, abilities to tunnel V4 over a V6 underlay. I think in your case, what you probably do want is more like a static XLAT because these are more for I'm running a complicated service provider network.
Yeah, actually, it's interesting. You don't want it static because then I've got to offer V4 static addresses to the client. What I want is the dynamic on the payload. I want to lie to the payload and tell it it's got a V4 address, but actually have that execute out as a V6 and then get mapped to a v4 at the edge if I have to handle inbound 4 traffic, right? So it's it actually gets carried as v6 and just gets de-encapped into whatever v4 I've told the pod it has, and that might get reused. So it's not really static; it is more dynamic. So
yeah, the map and Lightwave 4 v6 are sort of fairly sophisticated ways of doing that. And again, it's when you're looking at the problem of running v4 over v6. There are a lot of ways to do it, and they have varying levels of complexity depending on your varying levels of need. Because one of the other options is, it's just simply something like a VXLAN GP NCAP, for God's sake, right?
Yeah, we can have a long conversation on that, but I think, Ken, I think this is one that we should probably start talking about in the network working group. Is it's sort of the v4 considered harmful RFC. We've gone from we don't support v4 to very quickly. Should we be talking about you should be considering v6, at least considering v6 only infrastructures if you're going to be at scale, and therefore what do you do with all your v4 endpoints, required endpoints in that environment? I don't know.
Well, I mean, one of the other things I can offer you guys as potentially something we could do is, I'm sure it will come as a great surprise to you that I have an incredibly deep v6 expert in my back pocket. I mean, you would never expect that, but I can literally persuade Mark Townsley, who is literally the fellow at Cisco who has been driving the v6 boulder up the hill.
Yeah, I know Mark really well from the I was an Ops v6 and everything else. So, Mark would be a good one to possibly pull in. But I think we've sorted these problems enough in the IETF. We know what can be done. It's just going to be a matter of implementing it in an efficient manner in the data plane. Because right now the options to do it in the data plane all sort of suck from a performance standpoint.
Yeah, and the good news is, I think you'll find the ones that we have don't suck. And if somebody decides they need more than what we have, they're tunable, meaning that with a little more elbow grease, folks can make them go faster. And because the release cycle in FIDO is about 3 months, and because it's running in user space as a microservice, you don't have to wait however many years for the kernel to catch up.
Okay.
And there are also some other options in here that may make life better. Like, I don't know if you're familiar with what IOAM does.
IOAM?
It's basically in-band telemetry. So you can optionally say, I would like to include an IOAM header with my traffic and get timestamps of every node that it passes through, including it went into your application at this time and data came back out at that time. So lots of
that's interesting for a NFV application. I think what we're going to see in Kubernetes land and cloud native land is a lot more of that happening at the L5, L7, i.e. like in the Istio layer. But it's still an interesting tool in the tool bag.
It is, but I mean, for example, being able to understand what is your latency tax from Envoy or from whatever your proxy is also may be of some interest if you're trying to figure out where things are going wrong. Anyway, that sort of features. In terms of feature velocity, this is just sort of showing we do releases every 3 months or so, and we pick up a fair number of new features every 3 months. And then, we have sort of...
Can we go back to that one real quick? Sorry.
Of course.
BFD fib, not 64 GRE over IPv6. Okay. All right.
And then we got the standard sorts of things you would expect from a relatively well-run project. When a patch is submitted, it goes through an automated verify where we run sort of hundreds of unit tests, hundreds more system functional tests, and then a fair number of, depending on how concerned people are about the patch, performance tests that get run on bare metal, so that we can make sure we're not seeing performance regressions in the entire system. And that happens before we even get to a code review step.
Got it.
And then once we do merge for usability, we publish a bunch of artifacts. So you get apt installable Debian packages, yum installable RPM packages, auto-generated documentation, that gets generated merge by merge. So you can always go apt-get or yum install the latest packages. And then per release, we also auto-generate test reports. We've got Puppet modules, there are training and tutorials, hands-on use cases, blah, blah, blah.
All right.
Yep. So then this sort of is trying to draw the picture here when I keep saying networking as a microservice. So you can literally run on a node a VPP vSwitch microservice pod. It would be bypassing the kernel to get to the NIC. And then it ends up providing networking for the individual pods that you're running as workloads on that node. And this gives you a lot of advantages. Basically, it's pure user space. You can talk directly to the NIC using DPDK. It ends up being quite a bit faster than what you get from the kernel. It's more scalable. It has a bunch of additional features. It evolves more quickly because you've got releases every 3 months. And since it's essentially just another daemon set that you run to provide your networking as a pod, upgrading becomes much simpler. You don't have to upgrade the underlying kernel in the box. And it also becomes a few milliseconds of restart on the pod as opposed to 15-minute reboot times. And all of this makes it easier to get faster innovation in the data plane as well. Good.
And I guess just to quickly round off the other question I asked before about public cloud compatibility, this is just a question from out of my own ignorance around the universal availability of DPDK. I take it that's just has been and is commonplace in.
Yep. So you're basically asking what happens if I'm running this in a VM instead of on bare metal, right? Yeah. So if you're running it in a VM, you have something that, as far as the VM is concerned, looks like a PCI NIC. And there is a UIO PCI generic driver that will work in that case. So even if you don't really have hardware there, you should be able to run this inside a VM in a public cloud.
Okay.
Plus there are also various efforts going on in public cloud as they're trying to address some of the NFV use space where they're actually looking at providing better DPDK support than that.
Okay.
So this is something that is public cloud friendly.
I have a question. So you mean to say this VPP will be in your pod and all other pods will be connected to that VPP?
Yeah, in this case, these connections are logical. I've got the next slide actually talks a little bit about the two options that you have available for actually doing that plumbing.
Okay, I will. Okay.
You consistently ask me good leading questions that take me to the next set of slides. Thank you.
Yeah, I mean, I was curious to know what if the VPP is outside, just we have the VPP virtual switch instead of in the pod. We can deploy the VPP in all the nodes and we can connect the pods in VPP as well. I was thinking like what will be the advantage of implementing in a pod actually. That's the reason, yeah.
Yep. So, okay. So I mean, let's go to this sort of next picture because this talks about how you can communicate with pods from VPP, right? So, and there's sort of two options that are available to you. One is you can use VETH pairs. And the problem with VETH pairs is they're comparatively slow and comparatively non-scalable. And so that's certainly an option. It's an option that will always work. And you will still get advantages from using VPP in that case. But one of the problems that we've seen repeatedly with various things with VPP is if you process packets really, really quickly and the I/O can't keep up, in other words, the links can't keep up, you're leaving a lot of performance and scalability on the table. So one of the options that we actually offer in VPP is we have a VPP user space host stack that implements TCP and UDP and that kind of stuff. And that host stack has an LD preload shim available so that with no code changes to the pod, you can actually slide that LD preload shim under for non-statically linked workloads. And you can then take advantage of the VPP user space host stack. Now this host stack scales to 10 million simultaneous connections, 200,000 new connections per second on 2 core. It's also been clocked out pushing north of 100 gig per second between two pods running on the same server on a single TCP connection, or a single connection. Because one of the things that we do is, if we detect that two pods are running on the same host, and you're using the VPP host stack, rather than pushing that traffic through a TCP stack, we simply treat it as a FIFO queue. And so you get really, really sped up performance there. So that's one set of options that will work with existing workloads out of the box. If you have workloads where you care for many...
Ed, that's going to cross namespace boundaries, right? You're not going to be constrained by a namespace boundary there.
Yeah, no, exactly. So if you're using these, then you're playing in the kernel namespace game. If you're doing
right.
You still have a namespacing concept, because you do have this is who is allowed to talk. These are the containers that are...
I'm talking about the VPP host stack. If the pod is in a tenant namespace, or C group, / network namespace, the vSwitch microservice pod is in the host namespace. The VPP host stack will span those namespaces, correct?
Well, keep in mind, if we're not running a VETH pair, we're not dealing with network namespaces anymore in the kernel sense.
Okay.
We are still enforcing the namespacing boundaries, because you still have a pod.
No, I understand that, but now that means changes to CNI and other things.
It doesn't necessarily mean changes to CNI. We don't mind that the network namespace is set up. We still give you the same isolation that you get from the network namespace.
No, I understand we get the same isolation. The question is just the change. If we can use because it's going to get a pod namespace is going to get set up for the thing. And in a model I'm looking at, the vSwitch microservice pod would be in the host namespace. So as long as the VPP host stack can span those namespaces, those network namespaces. I know it's not necessary for keeping, routing table, etc. I don't rely on any of that. That's the way things get done. So long as you don't have to change that plumbing, that's a little bit easier.
Yep. So that basically. Now, there's one other aspect of this. If you are dealing with a workload that is sufficiently performance sensitive that you actually, so here's a fact about the world that anyone who's tried to write a high performance TCP stack has eventually hit, which is that the BSD socket API itself is a bottleneck. The API itself limits performance when you get to the far out edges. And so if you have an application where you are finding the BSD API itself in this situation is creating a bottleneck for you, we do have a higher performance native API that is available if you wish to use it for your workload, but it would require code changes in the workload. So for example...
I'm not so much worried about that. I'm just worried about trying to avoid the VETH pair to get into the pod if I could.
Yeah, absolutely. And so we've actually gotten, I'll point you to this. We actually do have examples of this working right now that I can point you to.
Cool. That's fine. Just if you can, send me a pointer, it'd be good.
Yeah, absolutely. So that's sort of the generic how you communicate with pods. And you've got the two options there. Now, in terms of how you communicate between pods, if you use the native space host stack, there's an interesting other thing that is possible here, which is the way VPP sets up the communications. Say you've got one pod listening and another pod connects to it, and they happen to be on the same host. It essentially is just acting as the broker here that sets up a shared memory segment between them. And once you've got that direct shared memory connection established, VPP gets entirely out of the way, because all the things that are done about authorizing the connection, setting up the connection, those go through VPP to control issues of policy and whatnot. But there's no reason that we have to touch every byte that passes through in order to allow you to communicate there. And you just save yourself mem copies by getting VPP out of the way once the connection's established.
So is all of the, so here's an interesting problem. If the config in VPP changes, i.e. somebody's added another policy and you've got pods talking over that policy, and Flyer changes a policy and you've got pods communicating with one another or using that policy in flight, this would bypass any policy changes. Somebody changes the Kubernetes network policy, for example, and that change affects in-flight traffic.
Do you mean changes the label on a pod? Because
Or they change the original policy said I'm going to allow 631 and 636 between LDAP clients and LDAP servers. Somebody goes in and drops 631, says we're only going to do LDAP S.
Maybe I'm misremembering, but I thought the last time I tried to actually change a network policy that I could not change a policy in flight. I could remove it and replace it, but I remember my attempts to change it did not go well.
Depends on how you're rendering the policy, right? Policy is just a Kubernetes object. It depends on what the network stack.
Right. But my recollection was asking Kubernetes to change the policy. Got back an error that indicated it couldn't be changed, but maybe I'm misremembering.
Well, in whatever way, if there is a change now,
yep.
By doing this, that is not going to be reflected, it looks like, on in-flight packets.
No, that's an interesting corner case to go take a look at and make sure that we get right. Yes.
Okay.
Cool. All right. So but there's a big pickup both in terms of the performance you can get between pods that happen to live on the same node, but also in terms of the cost of networking between them. So you get an increase in scale and density as well.
Okay.
And then I've been talking a little bit to Matt Klein about possibilities here with Envoy, because they're sort of an example of people who are very interested in the performance of things. And so in the Istio Envoy case, were you to use the VPP host stack, it's the same LD preload shim game involved. It's just that you're talking within the same pod over that direct shared memory once connection is established, instead of between pods.
Right, but you wouldn't be doing that between pods in Envoy anyway if you load the Envoy into a sidecar.
Yes, but you would be doing it between containers.
They're in the same network namespace. I guess, yes, but you could be talking to localhost, right? So, not sure. I guess it depends on how you're doing the localhost within the pod. I'm also a little confused here. You've got VPP host stack connected to both containers. The VPP host stack, I think, would be connected into the pod's network namespace, not into every container.
The network namespace is a kernel concept about how it partitions the kernel-owned interfaces. The VPP host stack in this case would be done via an LD preload shim.
Into every single...
Mm-hmm.
Oh, okay. This presents an interesting problem then for Kubernetes network policy, because Kubernetes network policy is a pod level, not a container level thing.
No, I know. The thing is, you still apply the policy at the level of the pod.
But I've got multiple interfaces for that pod. How do I map that? How do I know that both of those host stacks are the same pod?
You don't actually have multiple interfaces. So the thing to
realize, the drawing is wrong.
The drawing is misleading, no question.
Okay.
There's no question the drawing is misleading. Effectively, what ends up happening is you have a context for the particular namespace that lives within VPP, which happens to correspond to the kernel namespace, but doesn't have to.
Got it. Okay.
It says, here are the collection of IPs that are associated to this namespace that the TCP stacks that are the host stacks that are talking here can talk to. And by the way, one of them is the local host, which should be treated the way local host is treated, and which may say, oh, by the way, this one over here is the proxy and reverse proxy, because that's what Envoy is doing.
Right, because all of those things should have the same be appearing as the same IP address outside of the pod.
It should be appearing as the same IP address or set of IP addresses if one were to go
down. Same IP address, because pods have the same, or...
In the case of pods, you're 100% correct. They have one external IP address. But if, for example, you wanted to do something like direct server return, you could do that.
Okay, this is a rat hole. You and I should probably have a conversation.
Yeah, I would be very much in favor of that. But basically, my point is that yes, you're one pod, but there's the flexibility to do more in one IP per pod. But there's the flexibility to do more if you want to do interesting things like direct server return.
Yeah. Okay.
Yeah, and so then Kubernetes integration, there's some example Kubernetes integration going on in the Conti VPP and area. And that's built out of the Legato framework, which I think I had mentioned, which is built on the Go VPP library. And there'll be some demoing of this at KubeCon, but I want to be really, really clear. This is an open innovation regime. There is no reason that other providers can't integrate with VPP. That's partially why the Go VPP library is separate from the Legato framework, is separate from the Conti VPP agent. Is if all you want to be able to do is use write a Go agent that talks to VPP or integrate VPP into your existing Go agent, you'd probably pick up the Go VPP library. If you wanted to do something that has some other niceties because you're starting from scratch, the Legato framework may prove to be useful to you.
Okay.
A lot of thought went into the how do we make it as easy as possible for everyone to play. Cool.
Okay.
And then just as a teaser, so IPv6 is a lot more than just addresses, right? Everyone sort of winds up there because of more addresses, but it also enables a bunch of other things that could be done implementation-wise to provide some of the existing APIs that we have in Kubernetes. You know, for example, being able to use MNEcast for smart load balancing, where you can actively measure not only the network latency to who you're talking to, but the responsiveness of the client in order to make your selections for who you're actually load balancing to. You know, the instrumentation I mentioned with IOAM already. If you followed the segment routing network programmability RFCs, there's a lot of interesting things available there. And of course, moving away from overlays and NATs to provide service for things like load balancing for services and so forth. All these are available implementation level options that don't necessarily require any change in the contract, which needs to remain simple to the actual consumers of the Kubernetes API. And of course, all of these are supported today at VPP, at high performance and scale. So you have a bigger palette to play with when making implementation decisions, is I guess the underlying point.
Yeah.
And then you can sort of weigh your trade-offs and make your calls. And then finally, the ubiquitous get involved slide.
Yeah.
I mean, Fido is an open community. We have literally days of tutorials if you want to code in it. We've got binary packages you can install, mailing lists, IRC channels. The good news about the wiki is anything you could possibly want to know is in the wiki. The bad news about the wiki is anything you could possibly want to know is in the wiki.
Yeah. Ed, are you going to be sharing these slides?
I'd be delighted to share these slides wherever it makes sense to share these slides. It's not clear to me where the right place is for the network working group.
GitHub, I would assume, Ken?
Where in GitHub is my question.
Yeah, and GitHub in the network work group.
Yep.
Do you guys have a folder for presentations or something, or?
Just if there's not, I can create one, but I think we've been putting them on the GitHub networking workgroup site, just linking them from there.
Okay.
This video will be uploaded on the YouTube, right?
Yeah.
Yeah. Okay. Cool.
Yeah. So we'll take offline figuring out where the right place to land them is, and then I should probably have a following up conversation with you, Chris, about many things.
Yeah. In the perfect world, that would probably be next week. But maybe if we don't get to it before then, maybe we do that in Austin. If not before, I assume you're gonna be at Austin, or are you not?
I will be in Austin. I will definitely be in Austin.
So yeah, let's try and figure out something if possible next week.
Cool. All right. Awesome. Does anybody else have any other questions? Surprisingly, we are exactly at time.
Yeah.
No, I think it's great.
Ed, this was good. I'm still digesting a bit. I think that the last 5 slides were probably where the meat of kind of my interest lies. Part of the you called them out in a few places, but there may be more to this. Just it was clear that some of the compelling reasons why those that are running workloads within an orchestration system like Kubernetes would come to use.
Performance, density, and scale are really big ones.
Yeah.
Particularly density. I mean, my friends at Intel tell me that they will shortly be giving servers that have 200 plus cores, and being able to do service, and I guess the scale speed guys are talking about a goal of being able to support 10 pods per fork. So you sort of run the numbers, and what you realize is that you have the thousands of pods density, and so you need something from a networking point of view that can support that. And where we're not quite there yet, we're rapidly moving now.
Yeah. Okay. Yeah.
Because I mean, and the density argument is a pure capex argument. If you can run the same, if you can increase the number of workloads per unit, whatever, you're in better shape.
Yeah.
So the Conti VPP is the Kubernetes network plugin, right?
Yes. Conti VPP is the network plugin.
Okay.
Yeah,
I got that GitHub actually. I'm looking at the GitHub. Yeah.
Let me go ahead and actually I'll stick the link in the chat for that just so you get to the right place, because there's some other development that's a bit older. So
Okay.
let me stick the link for that in the chat so see if they have it. One moment, because I have lost there we go. That would be when you go to look at the Conti VPP stuff, and this keeps back in front of us about, there's an example I can point you to with this sort of thing.
Okay. Thank you.
Thanks, everyone.
All right. We're time for the piece of culture. Thank you so much.
Thank you, guys.
Take care.
And Ken, I just created a presentations folder. I'm going to do it as a GitHub pull request to you.
Okay. Thanks.
Cool. Thank you.
Talk to you later. Bye-bye.
Bye.